going to do some examples for directional derivatives and gradients. So, our first example, we have f of xy equals tangent of x minus y over x plus y. We want to find the gradient. So, we got to find our x derivative. So, we use chain rule, secant squared x minus y over x plus y times the derivative of the inside. So we can do quotient rule for this. Bottom derivative of the top with respect to x minus the top derivative of the bottom with respect to x over the bottom squared. We still have the secant squared. So if we combine the terms on the numerator, we'll get 2y, because these x's will cancel and the y's will add. So that's our x derivative, and our y derivative, df dy, we'll have secant squared again. D dy, the same thing. So now we got to do the quotient rule again, this time with respect to y, so bottom derivative top with respect to y, which is -1, minus the top derivative of the bottom with respect to y over the bottom squared. That's going to be we're going to have negative x and a negative x, so minus 2x, negative y and positive y, which is 0, so they cancel. And we still have our secant squared. And this is our y derivative. So our gradient, which is our x derivative comma the y derivative, will equal secant squared x minus y over x plus y times 2y over x plus y squared, comma secant squared x minus y over x plus y times negative 2x over x plus y squared. And we can factor out 2 secant squared x minus y over x plus y over x plus y squared. And then the inside of the vector will just be y times y negative x. And that's the gradient of f. So, next example.
Part-time love is the life around here. We're never done. Everything feels like touchdown on a rainy day.
We want to find the directional derivative of f, where f equals f of xy x squared times sine y at the point 1, negative 1, 0. And we can write this with curled brackets. So we got to find gradient fx comma xy. So fx is just the x derivative of that, so 2x sine y, and fy is the y derivative, so x squared times cosine y, and our directional derivative here is going to be gradient times the unit vector Well, our unit vector is just going to be oh, sorry, I didn't specify the direction. So, in the direction of 2, -1. So, the unit vector is going to be this vector divided by its magnitude, which is going to be 2 squared of 2 squared plus 1 squared, which is 4 plus 5. 4 plus 1, which is 5. So this is our unit vector. So this dot product is going to be the dot product between 2x sine y, comma x squared cosine y, dotted with 2 -1 square root of 5. So that's going to equal 4x sine y minus x squared cosine y, all over square root of 5. But we want this at the point it's -1, 0, so if you plug in -1 for x, we get -4 sine 0 minus -1 squared cosine 0 all over square root of 5. This is just going to be 0 in the x component and -1 in the y component. Or sorry, I messed this up. Go back here. Since this is a dot product, we're adding these two components together. So now if we plug in this, we get -4 sine 0 minus -1 squared cosine 0. Sorry about that mistake. So we're going to get 0 minus 1 over square root of 5. This is just going to be -1 over root 5. Because this has to be a scalar quantity, not a vector. So now, third example, in which direction does f of xy equal e to the x cosine y increase the most rapidly? At the point 0, pi over 2. So we got to find the gradient. So the x derivative is going to be e to the x cosine y, because nothing changes with that. And y derivative is going to be negative e to the x sine y. Derivative of cosine is negative sine. So we have e to the x cosine y, comma negative e to the x sine y. You can factor out e to the x. So now we got to evaluate the gradient at 0, pi over 2. So we plug in 0 for x and pi over 2 for y. Cosine pi over 2 is just 0. Sine pi over 2 is 1, so we get a -1 and a 0, and e to the 0 is just 1, so the direction is going to be the unit vector for this, but if you look at the magnitude, or if we divide it by its magnitude, we'll see that its magnitude is already 1. So this is the direction. And it's a negative y direction. So now, last example. We want a unit vector normal to the level curve of f equals xy at the point 2, 3. So our normal vector is going to be equal to the gradient. So fx is just y, and fy is x. So we have yx. But we want the normal vector at 2, 3. So this is going to be 3, 2. But we want the unit normal vector, so we're going to divide this by its magnitude. So square root of 3 squared plus 4 squared, or 2 squared. That's going to be 9 plus 13, or 9 plus 4, which is 13. So this is our unit vector. And those are the examples.
Part-time is the life we're living. We're never done. Everything feels like touchdown on a rainy day. Part-time.